The Division of Radiophysics has its main headquarters within the grounds of Sydney University. Here are provided extensive laboratories and facilities for research and measurement, particularly at ultra-high frequencies, and in addition facilities for the design and construction of experimental equipment required for this work. The laboratory was established just prior to the outbreak of World War II. Many special types of radar equipment were designed and developed to meet the special needs of the Allied forces in the Australian and the Southwest Pacific areas. At the end of the war, the picture changes. The division's program and its organization and facilities were reoriented towards the peacetime application of radar techniques and fundamental investigations in the newly developed region of ultra-high radio frequencies. The current activities of the division can best be shown by considering in turn the major researches which are included in its present program. It has been discovered that the sun and other celestial bodies emit radio waves, as well as light and heat. The stars are at very high temperature, and the atmosphere of our nearest star, the sun, is in a state of unceasing activity, as shown by these speeded-up records taken at Climax Observatory, Colorado, USA. This new branch of science, which is being actively pursued in Australia, and which is concerned with the study of radio waves from the sun and stars, is called radio astronomy, because it makes use of radio equipment rather than the more familiar telescope. Special aerials are used, covering frequencies from 60 to 30,000 megacycles per second. They vary in size and shape according to the frequency on which they are used and to the particular purpose for which they are designed. They are usually supported, like telescopes, on equatorial mountings, and are driven by motor so that they remain accurately pointed at the sun or star field being observed. The output from the receivers associated with them is recorded automatically on pen recorders. The sun, of course, is the subject of special study. The intensity of the solar noise, as it is called, increases when the sun is active, usually indicated by the presence of sunspots. And most of this enhanced radiation has been shown to come from the vicinity of the sunspots themselves. Sometimes the recorders show sudden increases in activity. These are called bursts, or when they are very great and of longer duration, outbursts. Now, do these bursts occur on all wavelengths? At Penrith Field Station, the characteristics of these particular signals from the sun are being studied over a range of frequencies. A special wideband rhombic aerial is used in conjunction with a receiver which 3 times per second tunes from 70 to 130 megacycles per second. A cathode ray tube, which can be photographed, automatically shows how the bursts vary in intensity. In this record, 70 megacycles appears on the left and 130 on the right. Although some of the aerials used have very narrow beams, this one, for example, only about 1 degree wide, this is not narrow enough to determine precisely the directions from which these radio waves are coming. Interference methods are therefore employed. In one method, 2 or more identical aerials, spaced an accurately known distance apart, are combined. This work is being done at a field station on the edge of a reservoir at Potts Hill. At Dover Heights, on a cliff site 250 feet above sea level, an alternative method is used, particularly for the discovery and identification of what are known as radio stars. For this purpose, the aerial is usually pointed at the horizon. As the point source of radio noise rises above the sea, the direct signals and those reflected from the flat surface of the sea produce a well-defined interference pattern at the receiver. By this means, some distant nebulae, for example the Crab Nebula, have been shown to be powerful sources of radio noise. As more sensitive equipment is being brought into use, more and more radio stars are being discovered. At least 20 are known at present, most of which do not coincide with any known visible objects in the sky. This is why they are referred to as radio stars. The moon gives rise to radio waves, but these are extremely weak because the moon is at a very much lower temperature than the sun. They can be measured by using special aerials, and they reveal how the moon's temperature varies just below its surface. From this we know that the moon's disk is probably covered with a thin layer of volcanic ash. The moon can also act as a reflector for radio waves and allows us to study what happens to radio signals when they pass out and back through the complete depth of the Earth's atmosphere. Through the cooperation of the Department of Information and the Postmaster General's Department, special signals are sent out from Radio Australia, which is situated at Shepparton, Victoria. These are picked up at a receiving station at Hornsby near Sydney. Under suitable conditions and when the moon is exactly in the aerial beam, the signals can be picked up again after they've travelled to the moon and back. A group of quarter-second pulses is sent out every 6 seconds. They are recorded on a cathode ray tube and can be both seen and heard. The loud pips, of course, are the outgoing transmissions, and the weak ones, about 2.5 seconds later, radio echoes from the moon. Notice how the echoes vary in strength. Some of these variations arise as the signals travel through the Earth's outer atmosphere. Radar waves can be reflected or scattered by water drops, and so radar is sometimes used to detect approaching storms and to track their movement. This speeded up record of the radar screen shows rainstorms forming and dispersing off the coast near Sydney. The laws of scattering of radio waves by water droplets are being investigated in the laboratory. Drops of known size are placed in a waveguide, and the amount of energy they reflect is measured. The echoes from raindrops in individual clouds are also being studied and are picked up by this aerial. The strength of the echo and the height within the cloud at which the reflection takes place is also measured. Independent measurements are also made of the size and number of drops in rain and in cloud. This is done by sending aloft a special microphone attached to a balloon. Raindrops impinging on this microphone modulate a carrier wave and are recorded by telemetering equipment in the mobile laboratory. In cooperation with the aeronautical research laboratories, now of the Department of Supply and Development, model aircraft have been developed whose flight can be controlled by radio. Flying models such as these are able to be directed from the ground and carry instruments whose readings are radioed back to the ground. These models have useful applications not only to meteorological investigations, but also to aeronautical research. The division is studying the physical conditions which exist within clouds, and the formation of rain both by natural and artificial means. These speeded up records show clouds forming and dispersing. Under suitable conditions, rain may be precipitated by treating clouds with various substances. The material most often used is solid carbon dioxide, commonly known as dry ice. The dry ice is first broken up into small pieces and loaded into a plane. The Royal Australian Air Force is cooperating by providing flying facilities for this work. The aircraft carries a downward-looking radar, which is used to reveal whether rain forms within the cloud after seeding. Flights are made when conditions for the formation of cloud are favourable. The plane takes off and makes for the nearest suitable cloud area. Physical conditions in the air at various heights are recorded, and when the cloud to be treated has been reached, it is first photographed from various aspects. The aircraft then circles above the cloud using the radar to check that it does not already contain raindrops. When all preparations have been made, the dry ice is placed in the chute and the aircraft makes a run at the cloud, where it drops the dry ice at a predetermined spot. The action of the dry ice is to freeze the cloud droplets in its path, and so form myriads of tiny ice crystals, which under favorable conditions grow rapidly in size and finally melt to form raindrops. The aircraft remains above the cloud to check the results. The radar in the aircraft shows rain developing and allows the process to be followed and recorded as the raindrops form and fall through the cloud which has been treated. Deep cumulus clouds, whose tops are much colder than freezing, are most likely to produce artificial rain in this way. In many cases it has been shown that the cloud seeded with dry ice rained soon after, while other similar clouds in the vicinity did not. The use of modern electronic and high-speed relay devices can effect a great saving in the mathematical work arising in physical and other researches. For its own special needs, the Division of Radiophysics is developing an electronic computer. In a computer of this type, many hundreds of relays and electronic valves are used. Mercury delay lines are used as the memory unit for the storage of numbers which can be extracted automatically when required. The machine receives its instructions and supplies its answers on punched cards and is used in conjunction with standard hollerith punched card equipment. A number of radar aids to aircraft navigation and airport control have been developed by the division. Distance measuring equipment and multiple track range are two of these. These consist of separate airborne units and radio beacons on the ground. Distance measuring equipment has been adopted for use throughout Australia by the Department of Civil Aviation. It provides a pilot with a continuous indication of his distance in miles to selected points along his route. These points are identified by code on a flashing neon lamp. The Australian multiple track range is a track guidance system for use along air routes and at airports. It provides a number of tracks radiating from an airport from which a pilot may select the particular track along which he wishes to fly. An indicator tells him when he has reached this track, and a sensitive meter on his dashboard then takes over and allows him to follow that track accurately. The aids to airport control, which have been developed by the division, include a radar set installed on the airport at Mascot, Sydney. This provides the traffic controller with a visual plot of all aircraft within a range of 20 miles. Another larger radar is situated at a convenient site away from the vicinity of the aerodrome. Information from this set is relayed by radio link to the control tower at Mascot. This provides the controller with a PPI picture showing aircraft up to a distance of over 100 miles. Because of the operational ceilings likely to be in common use with jet-engined aircraft, it is important to know the structure of winds at heights above 30,000 feet. The division is using radar methods to track balloons to great heights. A special silver-coated balloon, which reflects the radar waves, is first inflated inside a larger balloon. This larger balloon provides a high initial rate of ascent. When the balloon is released, it is followed and plotted with a theodolite, as it is not very discernible on the radar screen at such close distances. When it is beyond the range of the theodolite, the high-power radar set takes over, and the echo of the balloon is observed on the radar screen until it finally bursts, sometimes at a height of 20 miles or more above the Earth's surface. As a result of these experiments, it has been found that the wind reaches speeds of up to 150 miles an hour at heights of 40,000 feet and above. Information of importance to future stratosphere flying.